All right, life in the pipes, man. In the breach once more, my dear friends. All right, so we're going to do this up here. Bringing minute physics up to the game. I need to bring him in here on this last page that we've been doing here. I've been working on my functional analysis for the field theory in field Newtonian limits for dimensional analysis while dealing with the wave particle, the 50 cal here, which is going to be hopefully you see me building this over this kind of new book review that I'm doing as I'm building it. To integrate this is going to be a heavy particle physics on applied physics, systems and engineering, physical engineering, wind particles of calculus models, again for the Fermilab spin direction, potential spin direction, measured directions, and things like that are going to come up real heavy with cicada alpha beta measurements. The way you describe a particle, how that particle is a photon, is a Z boson, is a Higgs, is a photon, a graviton, at any rate here, I had to change some things on the original standard model to get it working this way in terms of the Hadron Collider to the apple to the photon experiment from our key of the ball and air, ball and water, ball and oil or fluorohydramonium acid. Remember, measurements may be alpha or beta in terms of what timelines and functions when we get into this stuff over at CERN and Fermilab for a key base. Now, I'll teach you how to kind of level and lattice some structures, some polarized EM waves, which are going to be important for the calculus we're dealing with at the speeds we'll be traveling for the types of mathematics of changing fields over and acting in the XYZ or XY functionality of graphing the positions of throwing the apple from the limits and measurements that we give it based on what the field ratios are for some of these equations and how to describe, again, some of those actions at spooky distances, here being the WIMP particle to the neutralino, the graviton, and I forget what the V one is there, to the Z boson collision type stuff. We have to first get past the first pipe drag, right? Because that drag's going to create some Lindenfrost effects of a ball in water dropping with zero resistance because it's creating an air barrier and a teardrop type aspect, right? So mind the topology, but it's traveling down the pipes to eventually bottom, make a collision at the far end, the end of the experiment, minus some of the factors that we'll be getting into, a shift in the anti-top, a different time ratio where I have to set the scales or the distances back given the compositions of metals or how much I can do. It's going to say what size Hadron Collider for this experiment, dropping an apple, throwing an apple, or gauging off of a photon in the pipes, moving at all kinds of. What are you doing with the measurement of what this is here? Applying on some heavy timelines against the practical level as well. In terms of, I don't have all day, I don't have all night. You can't just throw out the baby with the bathwater and throw out some numbers, whether it be some of the numbers or a sum, the form where I need values. I need some kind of interpretation of a scale into this next drawing in terms of break down the problem, throw out some of the numbers, bound the problem. So here I'm binding this problem. I'm basically saying in this field, if it works this way, it would be practical in describing what dark matter particles are, or at least certainly be able to be useful and interesting while describing what the physical of actually putting it into some EM jar over there at CERN would look like. Because when I say physics, there's a lot of different experiments that determine what physics is using this piece of equipment, or what an apple can do, or what your visually IH photon cicada numbers to stuff sliding around on here for Pensrow traveling through stuff and Well, Miniphysics here getting about particles.
Thanks to Google for sponsoring a portion of this video, for supporting small businesses, and for helping people find jobs.
They work in the same speed lines as these experiments because what reaction? G1 is what I wanted.
Atomic orbitals have long been a source of frustration for me. On the one hand, you have simple cartoon diagrams
aspect of that ball for how much it'll bounce for a mechanical reason. Maybe it's a test to determine the density or plasticity reverberation of that piece of metal or silica in a form.
But they're still very much just cartoon stand-ins for the vague idea of atom. On the other hand, you have atomic orbitals depicted as fuzzy clouds or balloons or rainbow donuts, which are definitely more technically
and later on he gets into this conceptual model very well.
But none of which feel like they give
but like I said, the visual optic, let's talk about that WIMP particle right here in the jar, about how much energy it takes up the majority of the field, 80%. Of what actually happens in terms of the strong force, the weak force, what is visually gravity, what is again this relationship between a macro and micro. Are we looking at Fermilab from the top or down the pipes here?
And yet also represents the very real idea that the planets all orbit the sun in roughly the same plane.
And they don't.
And there's
all kinds of junk inside here moving.
And if it's animated, we get to see that the closer planets complete their
orbits. But the zero ratio spin each other about. You know, we're talking about these things.
A good picture.
Zero. This is as much the Big Bang as.
Some of them because they're important for the physics of atoms, and some of them because they're questions my brain wants answers to.
All right, so this helps you visualize what that atom, the wobbles on the Plug Incorporated board.
Relative to other pictures.
Right, so anyways,
of course, the wave
that's the reaction you're trying to catch that. Oh, it's grinding on the pipes coming around it. Or as I'm ramping it up to skip the WIMP particle, which is the first step, which becomes skipping the collision to get it to go around the pipe once, separate differences, or however they make the collision happen, to ramping it up on speeds, increasing later heavier particles and centrifusion
here's what you get.
Values that would put it into a range like this and give me, field strength inversions. It would give me the inversion constant. It would give me what beta radiation is by a value inside here to gamma. Gamma being the most deadly on the index 1 to or alpha, in whatever case that may be.
And they're all mesmerizing and beautiful.
Relative, stand next to a neutron star. And again, so a lot of that point, a lot of here too, is condensing megabytes, generalizing the problem, and like neutrinos, you want to condense all this material down in their neutral value of Higgs separated with spin for 0, so that way again I can harness that and then use that energy in a neutrino Dyson sphere, carbon graphene structure which conducts the slip inside here. Oh yeah, you get it. And electrons with more energy are more likely to be far away from the nucleus. And again, we're talking about a lot of things about the collision of particles of the atom. When you really break it down, I'm trying to make a collision like this because it'll act different with those things, and it'll increase the ratio in which I get the result that I want. Hey, you use an AR-15 and you got 100 yards at 600, right? But at a different range, a rock can do it.
And they're pretty. I hope you like them as much as I do.
Alright, so anyways, that was my note. I wanted to get in here. I'll be integrating some of
so if you want a cartoon representation of an atom,
Heaviside's theories for Maxwell's. Obviously, we integrated. We want to make sure we touch on Fermiday, Sue here, Gauss curvature, and Maxwell,
and then the third one, the electron is
Heaviside, and there's a few other ones in here as well,
Planck, which is why the dots aren't moving in the middle
whoever
orbital,
comes up in there. I tried my best to give you some of the names or put you on the reference. Part G, where does light come from? Starting with a photon. This is a good syllabus key
of an atom. But really, the beautiful 3D ones are where my heart is.
Catch you on the next one.